All right, so we've talked a little bit about contact and non-contact forces, and we've actually used some of those forces in problems that we're solving. We'll have a couple of videos here just about particular types of forces. And so we'll start with normal and tension forces, which we might think of as kind of push and pull. So that'll start us off. There are a range of common forces, and we've mentioned at least most of them. Um, we have applied forces, normal forces, which are a reaction from a surface to a force, tension forces, which are in like ropes, wires, strings, friction, and drag. These all involve contact between one object and another material. In this case, that material is a water or an air, but it's still a material. And then we have spring forces. And then we have a set of non-contact forces, such as weight force and electromagnetic force, which is this. We'll deal with this in 152. Everything else we'll talk about here today or have already talked about. Okay, so the first one we'll look at is the normal force. And this is not a phrase most of us are familiar with. Um, but the normal force is the reaction force when something presses against a solid object. So when I lay this bag of dog food down on a table, that's me right there. Um, what happens? Well, it stops accelerating, right? But we know gravitational acceleration is constant. So there is a weight force on it. It doesn't stop weighing or being accelerated towards the center of the Earth. What happens is there's now a balancing force. That normal force presses back up on the dog food and keeps its acceleration at zero. Um, the normal force always acts perpendicularly uh, the to the surface, right? So if my surface is here, that normal force is going to be pressing straight up. Now, if my normal force is at a slant, um, or rather, if my surface is at a slant, then that normal force too will be at a slant. It'll be perpendicular to the surface. What is the normal force? Well, um, when something rests on a table or on a ground or against any surface, there's some small deformation of the surface. Even if it's solid steel, um, there's going to be a small deformation. And that deformed surface wants to return to its normal position, right? So you can see this bowed table here. Once I lift that bag, it's going to return back to its straight, nice surface here. But it wants to do that the whole time. It's pushing back up on the dog food, trying to get back to its home spot. And that's what causes the, the force that keeps the dog food there. This reaction force is the result of atomic bonds. So the bonds holding that solid material together are at a distance they are because there's a balance in atomic forces. And so when I press down on it and push some of those molecules closer to each other, they don't want to be closer to each other. And so they push back. They try and return to their normal static state. One tricky question is if we think about um, a slanted surface. So if I have a surface that's like this, and let's draw a little person there. I'm on a scale. Okay, let's see, what color is my scale? My scale, oh, it's still, I was trying to make it purple. My scale is right there. How is it going to register my weight there? Well, what that scale is doing is it's measuring the normal force. It's measuring the amount of pushback um, that it needs to do to keep you there. So my weight force here, if we draw our free body diagram, let's see. Here's my free body diagram. My weight force, going crazy with the colors, is pointed straight down, like so. Okay. Um, my surface comes through here, and that means that my normal force is not directly opposed to my weight force, right? So how do I know what my normal force is? Well, I know I'm not accelerating in this direction, right? Okay, so I know there's a balance of forces. So my normal force is whatever the component of my weight force, should have made this a dotted line. Um, this dotted line here, it's this component of my weight force, right? My other component of my weight force looks like that. Okay. We know that this, go back here, this hypotenuse is always going to be bigger than this, right? So if I'm on a flat surface, my scale is going to read this force. But if I'm on a slanted surface, it's going to read this force because this is the force necessary to balance my normal force. And the scale is reading my normal force. So if I have a scale that's on a slope, it's going to tell me I weigh less. So if you ever want to lose some weight, just go take your take measure your weight out on a hill somewhere, and you'll feel better about yourself. So that's normal force. Okay, a tension force is a force that's transmitted through cords and cables. The interesting thing about a tension force is that it is always the same throughout the whole cord. Okay, so if I have a cord like this, my tension force on one end is going to be the same as my tension force on the other. And in fact, at any point in the middle, we could talk about the tension within the cord, and it would be that same T value. Okay, so this means that you can transmit force using a cord. If I pull on this with T, um, it's going to pull on this block with T as well, right? Because the tension within the whole cord is the same. And so it gives you a great way to transmit force from one place to another. Now, if I set up a pulley system like this, not only am I transmitting the force, say from here to here, but I'm changing the direction of that force because the tension in my wire is the same here as it is here, as here, as here, as here. Okay, and so I know that if I say put a certain amount of weight here, I can define how much force I'm going to be pulling on this block with. So that's the cool thing about tension force. Um, Now, the thing we have to say is that this is an idealized tension, right? We're assuming a kind of massless cord that doesn't have its own irregularities in it, that there's no friction in a pulley like this. And so if we actually measured the forces here and here, they would probably be a little bit different. But it's close enough that it works uh, in practice. But in an ideal world, it's actually always going to be true that that tension is going to be the same throughout a cord. So let's look at a little tension example. Uh, which is our tightroper over here, who seems to be having some troubles. Um, why is it that a tightrope can never be exactly horizontal? Why is that not possible? Uh, we can figure that out using the idea of tension and using a free body diagram. Um, if we look at this right here, okay, what are the forces on this point in the tightrope? Well, it's being pulled with a tension TR that way and by a tension TL that way and pushed down with a force W that way. So our free body diagram looks like this. Okay. Um, what happens if TR and TL are perfectly horizontal? That means that there's no counteracting force to W, right? And so if we wanted to calculate our force in the Y direction, we'd find that we had a net external force on that point in the rope that was directly downward. What would that mean? It would mean that that had to accelerate, right? Because we know that any body with a net external force that is non-zero is going to accelerate. So in order for this to be still, it has to be balanced by some y component of TR and TL. So they have to bend here, or you're not going to be in equilibrium. You're going to have some kind of acceleration. And then we might ask if the tension in the rope will be greater or smaller than the weight force. Well, if you look at this and think about these 5-degree angles or so, you're going to need a lot of tension in the rope in order to counteract that weight force, because it has to be strong enough that its Y component, which is going to be a very small part of it, right, is strong enough to balance W. So that T is going to have to be big. And we can do a quick calculation to show that, right? If we assume that the rope is not moving, that is that MA equals 0, and that this tightrope walker weighs 70 kilograms, we can say that the sum of forces in the Y direction are the Y components of the two tensions, okay? We can see that in our free body diagram, minus the force weight, which is going to be in the negative direction, equals MA in the Y direction, but we know that's 0 because we said it's not moving. Okay, so then I can take these guys, I can move FW to another side, and I can recognize that TR and TL have to be the same. Why? Because that's the nature of tension, right? We know that tension within the rope is going to be the same at any point within the rope. And so I get rid of TL and TR and I just call them T. And so I end up with 2TY equals FW. That's just from moving force W over to this 0 side. And then I know that the Y component of T is going to be sine or cosine, right? Angle is here. I want the opposite as the Y component. Opposite is so, sine, opposite hypotenuse. And so I end up with the sine of 5 degrees equals FW. And then I can do some math here. 70 kilograms. This is the sine of 5, which is very small. And that means that my overall force here is going to be quite large. Okay, so that's like basically the force of about 400 kilograms. That's a lot of force in that tension. One other way to see this is to think about this example. If your car is stuck in some mud, one thing you can do is get a rope as taut as you can, you know, with the highest tension as possible, and tie it to a tree, and then push on the middle of it. And what that does is creates a much higher tension compared to the force here, creates a much higher tension in this rope or chain, and it can help you get your car out of the mud. So who says this class isn't practical? This may help you one day.